So let's talk about now how to find the pH of an acetic acid solution. And pH, we're going to see, is going to be the factor of two things. One of them is going to be the Ka, which is just a constant, and that's not a big deal. But it also depends on the concentration, the moles per liter. And these little animations here show 4 different pH values for acetic acid. And you can see how the concentration, as it gets bigger, going from top to bottom, the pH is getting more acidic. So the amount of acid plays a factor as well as the Ka. And we can figure out pretty readily how to determine the pH for these weak acids, and then weak bases later, of course, too. So here's a question you might run into. Let's say we have 1.00 molar acetic acid, and we know that acetic acid is a weak acid. It reacts with water in an equilibrium to make hydronium and acetate. If this was, of course, HCl or nitric acid, a strong acid, we'd use a one-sided arrow, but most acids we would use the equilibrium part. But anyway, we can use the 1.00 molar acetic acid value and the Ka from the table, and again, the acid and base table is in problem set number 2, but we can use that to find all these different things. We can find the concentration of the acetic acid that's left, we can find the amount of hydronium created, the amount of the acetate, the conjugate base that's created, and the pH. In order to do this, we need, again, an ice table, where ice, again, is initial change in equilibrium. We'll have the acetic acid followed by hydronium and acetate. We won't include water because water, again, is a liquid. No liquids and solids in equilibrium expressions. So if we start with 1.00 molar acetic acid, then the initial concentration of acetic acid, 1.00. In an equilibrium, the acetic acid will decrease and the hydronium and the acetate will both increase. Remember, in an equilibrium, you have positive values of all the reactants and products. So at equilibrium, 1 minus X for acetic acid and X for hydronium and acetate. Special note there at the bottom, water itself has a little bit of hydronium and a little bit of hydroxide. However, at normal conditions, it's only 10 to the minus 7, which is much, much, much smaller than 1.00. And in these kind of conditions, hydronium will also scoop it. So the amount of hydronium or hydroxide from water is negligible. We don't worry about it. Remember also the HOAC is acetic acid, that's CH3CO2H, and the acetate ion, OAC minus, is officially CH3CO2 minus, all right? And we're just abbreviating all of these things here. If you look up in the table of acids and bases, acetic acid is 1.8 times 10 to the minus 5, and that equals hydronium times the acetate divided by the acetic acid, just like all Kas. All Kas have hydronium in the numerator, they'll have the conjugate base next to it and the initial acid in the denominator. So for this reaction using the ice table, X was both hydronium and acetate, so X times X is X squared, and the acetic acid would be 1.00 minus X. Now, this reaction, X squared over 1 minus X equals 1.8 times 10 to the minus 5, that would be a quadratic equation, and you could use the quadratic formula to get the two values of X. And if you have the solve button on your calculator and you're good about putting things in, absolutely go for it. All right, this is a good time to do it. But there is a better way to do these problems sometimes, and let's talk about what those sometimes are. If you assume that X is a very small number, because again, these are weak acids, all right, they don't have a lot of hydronium, they don't have a lot of X, then 1.00 minus X is basically going to be just equal to 1.00. Remember that, as we talked about earlier, sometimes if you subtract or add really small amounts, it doesn't make any difference by the significant figures. And if that minus X right there is small, then 1.00 minus X is basically equal to 1.00. And that makes your life a lot easier, because if you can pull that minus X out, then you have 1.8 times 10 to the minus 5 equals X squared divided by 1.00. So again, what we just did there is we assume this little x right there is so small relative to 1 that 1 minus x is just equal to 1. And you can see that makes your life pretty easy. 1.8 times 10 to the minus 5 equals x squared divided by 1. So x squared would be 1.8 times 10 to the minus 5 times 1. X would be the square root, 1.8 times 10 to the minus 5 times concentration of acid. Let's abbreviate that. Square root Ka times Ca. Remember that something to the 1/2 power is square root. So you could also write this square root Ka times Ca, and that equals hydronium. And this is a pretty awesome expression. Now, Ca stands for the concentration, the moles per liter of our acid. In this case, it was 1.00, but you could put in any number you want. And as long as X is small relative to the concentration, hydronium equals square root Ka times Ca. So you don't have to use your quadratic equation or your solve function if this kind of relationship works. This relationship works really well almost all the time in our classes, all right? If it does work in this example, hydronium equals square root Ka times Ca, square root 1.8 times 10 to the minus 5 times 1.00. Remember, Ka, the number comes from the table. That's something you look up. Ca is the concentration of your acid, so 1.00 is the concentration here. So square root Ka times Ca, square root of 1.8 times 10 to the minus 5 comes out to be 4.2 times 10 to the minus 3 moles per liter. That's the concentration of your hydronium. That's also equal to the concentration of the conjugate base. Remember, those two were both equal to X in the ice table, so that number works for two different things. pH equals minus log of hydronium, so minus log 4.2 times 10 to the minus 3 equals 2.37. And again, the acetic acid here would just be equal to 1.00. It hasn't changed in this reaction because minus X was so small. Using this square root Ka times Ca thing is pretty freaking cool, and it works a lot of the time if 100 times K is less than C, all right? So if 100 times Ka is less than Ca, then you can use this hydronium equals square root Ka times Ca. So in the example we just did, Ka was 1.8 times 10 to the minus 5. 100 times that number would be 1.8 times 10 to the minus 3. And that number, 1.8 times 10 to the minus 3, is certainly less than Ca, which was 1.00. So in this case, absolutely, hydronium equals square root Ka times Ca. Now remembering that hydronium is related to pH, minus log of hydronium equals pH. pH equals minus log square root Ka times Ca. That is the ultimate way, most of the time, to find the pH of a weak acid. You must have 100 times K less than C for this to work. All right, if you don't have that, then you can't use this expression. But if you do, wow, one-stop shopping, pH quickly comes out minus log square root Ka times Ca. You must have 100 times K less than C. As 100 times K approaches C, this doesn't work as well. And then you should go back and use the quadratic formula, your solve function, whatever. But most of the time, 100 times K is less than C, and pH will equal minus log square root Ka times Ca. I love these kind of abbreviations because even those of you with your solve buttons, you're going to have a lot more work to find the pH. And if you can do this quickly when you're doing lots and lots of them, saves you a lot of time. So here's an example with formic acid, HCO2H. We have a 0.0010 molar solution of formic acid, and there's the Ka if you look up the table. And we want to calculate the pH of this 0.0010 molar solution. Well, this is a weak acid. It has a Ka, and the first thing you might want to do is go pH equals minus log square root Ka times Ca, because that is obviously less work than the other way. But 100 times K here would be 100 times 1.8 times 10 to the minus 4. That would be 1.8 times 10 to the minus 2. And the Ca, the concentration of the acid, is 10 to the minus 3. So using square root Ka times Ca here doesn't really work. All right, I said it's going to work most of the time, but I want you to see the conditions when it doesn't. All right, and 100 times K is not less than C. 1.8 times 10 to the minus 2 is greater than 10 to the minus 3, the Ca. So when you do the approximate solution in this problem, you get a pH of 3.37. If you do the exact solution, all right, where you'd have 0.0010 minus x in the denominator, x squared on the top, and all of that equal to Ka, you can solve hydronium that way, you're going to get different numbers. You're going to get 3.47, all right? You should not use the approximate solution here because, again, 100 times Ka is not less than Ca. The better solution by far here would be to use the 3.47. It's more work, but that's what you want to do here in order to get the correct value. So again, in this problem, the exact solution is better. 100 times K must be less than Ca. However, like I said, most of the time in this class, 100 times K will be less than C. You should go through and use square root Ka times Ca. Bases can be weak, just like acids can be weak. There's a whole bunch of different possibilities. Caffeine itself is actually slightly basic in coffee. It has a Kb value. There's also ammonia, benzoate, phosphate, etc., etc. You can find pHs from bases just as well as you can from acids. Let's look at an example with an ammonia solution, 0.010. Ammonia reacts with water. It makes ammonium and hydroxide. Hydroxide means this is a Kb. Ammonia is creating hydroxide. It's a base, 1.8 times 10 to the minus 5. Let's calculate the pH of the solution. No problem. So like before, ice table, ammonia, ammonium, hydroxide. Keep water out because it's a liquid. Initially, we have 0.010 molar ammonia. It's going to go down by x, so at equilibrium, 0.010 minus x. On the other hand, ammonium and hydroxide will both increase by x. So here's the different values at equilibrium. And we'll set all of those equal to Kb, like we did with the Ka in the last example. Kb 1.8 times 10 to the minus 5, that equals x squared on the top, 0.010 minus x on the bottom. And again, at this point, this would be a quadratic formula. This would be a time to get out the solve function and figure out, and that's totally fine. However, just like with acids, you can do a similar kind of thing. If 100 times K is less than C, you can pull out this little minus x right there. And sure enough, 100 times 1.8 times 10 to the minus 5 is 1.8 times 10 to the minus 3. 0.010 is 10 to the minus 2. So here, 100 times K is less than C. So if you pull out that minus x, then you have 1.8 times 10 to the minus 5 equals x squared divided by 0.010. X squared equals Kb times Cb, or the square root of Kb times Cb equals hydroxide. If you do that, hydroxide, 4.2 times 10 to the minus 4 moles per liter. If you use the exact values, all right, and this is what I did right there, you'll see that it still comes out to be the same. So again, as long as 100 times K is less than C, you can use these approximations in Chemistry 223. If you're using lots of significant figures in an actual lab, then you may be worth it to go through the solve function and figure out the exact versions based on the quadratic formula. But most of the time, 100 times K, if it's less than C, then you can pull out that little minus x, and the hydroxide in this case equals square root Kb times Cb. Just like we saw earlier, hydronium was equal to square root Ka times Ca. Again, all of this assuming 100 times K less than C. So in this problem, hydroxide, 4.2 times 10 to the minus 4. To get to pH, there's a couple ways you could do it. You could use Kw divided divided by hydroxide equals hydronium, and then minus log of hydronium would give you pH. You could also go hydroxide to POH, and then 14 minus POH would give you pH. Either way is fine. In this example, I went POH minus log of 4.2 times 10 to the minus 4 was 3.37, and then 14 minus 3.37 gave a pH of 10.63. By the way, you can check yourself. This is a basic solution, so pH should be larger than 7. This pH is larger than 7, so that's good. That's a nice way to kind of check yourself sometimes. If you really want to have your mind blown, all right, Eraserhead, I'm a David Lynch fan too, but I don't need to talk about that in detail. You can also use an overall expression. So for the weak acids, we saw pH equals minus log square root Ka times Ca if 100 times K is less than C, and that was a quick way to find pH. Well, for bases, pH equals 14 plus log square root Kb times Cb, and that's an alternate way to quickly solve for the pH of a weak base. Now, I love these expressions because most of the time in science we're trying to find the pH of something, and if you can use 14 plus log square root Kb times Cb, you don't need an ice table. You do have the Kb, you've got the Cb up there, you can just plug and chug. So this is an alternative way to do it. It may not seem that 14 plus log square root Kb times Cb is a quick and dirty, I understand completely, but it keeps you from doing an ice table, it keeps you from doing the quadratic, which only gives you hydroxide, and then you have to translate hydroxide to pH somehow. This is like one stop kind of thing, and I like it personally, but again, whatever you do is cool. However, you can use approximations if 100 times K is less than C. Keep that in the back of your mind while you're going through the problems in problem set 2, for example. Here's an overview of how to calculate the pHs of acids and bases. Strong acids, all right, all of the acid dissociates to hydronium. So literally pH equals minus log the concentration of the acid. If you have 0.1 molar HNO3, then minus log of 0.1 is how you're going to find the pH. And similarly for strong bases, all of the strong bases are turned into hydroxide. So just literally 14 plus the log of the concentration of the base will give you pH. If you have 0.1 molar sodium hydroxide, then the pH would be 14 plus log of 0.1. Now for weak acids and weak bases, if you can use 100 times K less than C, then pH is minus log square root Ka times Ca for the weak acids, and for the weak bases, as we saw, pH equals 14 plus log square root Kb times Cb. Those only work again if 100 times K is less than C. We're going to use these a lot, so I'm just letting you know. It's a good idea to memorize them / put in your calculators. We're going to be hitting this stuff pretty hard, not only in this chapter, but also in the next chapter too. But knowing how to quickly calculate pH can be pretty helpful. Salts, which are ionic compounds you place in water. You may not expect them to have acidic properties, but some of them do. And so what I'd like to do here is an example of what happens when you put ammonium chloride in water. All right, is it going to be acidic? Is it going to be basic, or will it truly be neutral? Now, we're going to think about both the ammonium and the chloride separately. So let's look in this example of what happens with chloride. Well, chloride, if it was to react with water as an acid or a base, it would steal an H plus to make HCl. It can't steal OH minus. Cl minus and OH minus would repel. But it can steal the H plus to make HCl and hydroxide. But if you think about it, HCl is a strong acid, and hydroxide is a pretty strong base. So if this was to happen, all right, then it's not going to occur because HCl would push it instantly back to the other side. HCl would go bam and push it back with a bigger arrow. And hydroxide would push back too and stuff. So chloride is an example of an ion that is going to make a neutral solution. And it's going to be neutral Not because it can't do something, like in theory it could make HCl, but it's going to be neutral because the conjugate it makes is so strong that the conjugate pushes the reaction back in where it was originally. Chloride has no pH effect, all right? So in this case then, yeah, chloride is going to be an example of an ion which doesn't have any effect on pH. And it doesn't have any effect on pH because its conjugate is a strong acid. Strong acid conjugates or strong base conjugates will push back in the opposite direction. But the ammonium, the other part of this ionic compound, is going to be different. Now, ammonium is the conjugate acid of ammonia. So ammonium in water will make ammonia and a little bit of hydronium. It is going to be a little bit acidic. Now, unlike in the last one where the conjugate base and the conjugate acid were so strong they push back, we're not going to necessarily have that here. Ammonia is a weak base and ammonium is a weak acid, and they'll kind of coexist here a little bit. So ammonium here is going to make the ammonium chloride solution a little bit acidic, and you can easily figure out what an ionic compound is going to do in water. You look at the cation and the anion, and a lot of the cations and anions will have Ks if you look on that table. Ammonium is an acid. It has a Ka, so that means this solution is going to be acidic. This will become really important because you might add ammonium chloride not expecting any pH effect, but what you're going to find, obviously, ammonium has a pH effect. This table here lists a series of neutral ions, and these things would not affect your pH. But notice there's also a list of basic ions and acidic ions. So adding a lot of these to water, you will have a pH effect. If you don't want to have any pH effect, you could have something like sodium mixed with chloride, or sodium mixed with bromide, or potassium mixed with chloride. Use ions on the left-hand side there. On the other hand, if you start adding phosphates or hypochlorites or sulfates, these kind of things, or even fluoride, they're going to create basic solutions. Acidic solutions can happen too. Ammonium is a great example of that because it's a weak acid. You can also add a lot of these hydrogen salts, or hydrogen polyatomic ions, I guess I should say. So like hydrogen sulfate will create a slightly acidic solution. Dihydrogen phosphate, etc., etc. Also notice down here, transition metal cations. Transition metal cations, we're going to see, also make acidic solutions. So be careful. When you add random chemicals to water, often you will have a pH effect. If you really don't want to have a pH effect, you've got to use things from the left-hand columns over here. But by default, most things do have a slight acidic or slight basic tinge to them. So the question here is, will a 0.1 molar sodium carbonate solution have a pH, and will it be less than 7, greater than 7, equal to 7? Well, to analyze a problem like this, think about cations and anions. And the sodium ion, all right, which is Na+, sodium ion is the conjugate of sodium hydroxide. And all the conjugates of those strong acids, strong bases will not affect pH. So the sodium ion here will not affect your pH. The carbonate, on the other hand, carbonate is not the conjugate of a strong acid or strong base. And if you look up in the table of acids and bases, carbonate has a Kb. It's actually a weak base. And because it has a Kb on that table, and B stands for bases, and bases are greater than 7, we would expect this solution to have a pH greater than 7 when you place it in water. So notice here what we did. We broke the cations and anions down and analyzed them separately. Conjugates of strong acids and strong bases don't affect pH. This is another reason why I wanted you to memorize those lists of strong acids and strong bases earlier. That means that sodium, potassium, and lithium, the conjugates of the strong bases, won't affect pH, as well as chloride, bromide, iodide, nitrate, and perchlorate, the conjugates of the strong acids. So sodium was one of those I just listed. That's not going to affect pH, but carbonate was not one. So then you can look at a table. You'll see that it has a Kb. B means basic. That means the pH will be greater than 7. You can calculate the pH of these solutions just as well as anything. So sodium carbonate here does have the sodium, which doesn't affect the pH, but carbonate does. Carbonate is a base. It's going to react with water to make hydrogen carbonate and hydroxide. And the Kb value for the carbonate, 2.1 times 10 to the minus 4. So like before, we can set this up in an ice table. Our carbonate is initially 0.10. All right. Carbonate's going to go down by x, while hydrogen carbonate, the conjugate acid, and hydroxide both go up by x. Notice that this solution is going to be a base, all right? So there's different ways you can go from here. What I would probably do is remembering that 100 times K has to be less than C. Well, 100 times 2.1 times 10 to the minus 4 is 2.1 times 10 to the minus 2. That number is less than 0.10. 0.10 is 10 to the minus 1. So you can just pull out that minus X if you want, and pH here, the hydroxide X will equal square root Kb times Cb. If you want to be really fancy, and because we're after pH, pH is 14 plus log square root Kb times Cb, but I digress. Now again, going back on what I just said there verbally, you can pull that minus X out because 100 times K less than C. 100 times 2.1 times 10 to the minus 4 is smaller than 0.10. So in that case, pulling out the minus X, hydroxide equals square root Kb times Cb. That comes out to be 0.0046. We're after pH though. So pH, you can go from POH to POH, or from POH to pH, or you can go hydroxide to hydronium to pH. Either way is fine. In this problem, I went POH minus log of hydroxide minus log of 0.0046. That comes out to be 2.34, and then pH would be 14 minus 2.34, which is 11.66. This solution is basic, as we hoped for and predicted, because it's a Kb, because it's creating hydroxide, because pH is greater than 7. Oh, it's all coming together. Now, that seems like a lot of work to me, so again, I'm going to highlight and recommend pH equals 14 plus log square root Kb times Cb. That's a quick way to do this. You just literally plug in the 0.10 times the Kb, 2.1 times 10 to the minus 4. You're all going to get high grades on the next test. I couldn't resist that very stupid and juvenile meme right there. But anyway, I think this will help. It's up to you. You don't have to do it. You can do quadratics, etc., etc. But again, if you want to make it easier on yourself, 14 plus log square root Kb times Cb, pretty cool. So here's some hints for studying for this chapter. And I'm going to have a separate page of equations here too at the end you can look at. But for right now, these equations will be really helpful to you. We already talked about pHs of strong acids and strong bases, and how to find the pHs of weak acids and weak bases if 100 times K is less than C. And we'll use these a lot. Also remember though that 14 equals pH plus POH, and 14 also equals pKa plus pKb if they're conjugates, and those come from the Kw expression. Kw, that 10 to the minus 14th, which is where the 14 comes from, is always based on room temperature. And if you study acids and bases outside of room temperature, you may need to retweak some of these. It's going to be really helpful to know the equivalence point pH values for titrations. Now, this is something that we talked about, but we didn't talk about it in this context. Equivalence point means moles are equal. And we talked about how if you have moles, equal moles of strong acid and strong base, the pH will be 7, neutral. On the other hand, if you have equal moles weak acid and strong base, the pH will be basic. That's what that means right there. If the moles are equal, what's going to be the pH range of the solution? And that will help us in the next section. It's also cool to know about formation constants. Remember, formation constant has the complex ion as a product, and the pieces that go into it are reactants. And then finally, Lewis acid and base theory does have a lot of implications. We'll talk about that. Just remember, Lewis acids are mostly transition metals, the group 3As and stuff. Lewis bases, always things with lone pairs. Draw the Lewis structure out if you're not sure. If it's got a lone pair on it, it's probably a Lewis base.